So hello everyone, I'm Vishal Singhani and my group members are Aniket Singh and Janvi Shetty. So our project title is Pancreatic and Segmentation using deep learning. The use of deep learning in AI and the medical field is one such field which has a lot of research potential and has a scope of developing something which is very important to society as well as can ease up the current process of diagnosing the existing disease and pancreatic cancer detection for the medical practitioners. So this is a research work and research project which is focused on the end goal of detecting pancreatic cancer, like the tumor part as well as the organ part from any MRI scan or the CT scan, which the doctor or the medical practitioner will be providing as an input. So we'll walk you over the entire process of data collection to data processing to model building, then model training, and then model fitting as well as model evaluation in this entire research work and the journey which we have followed in the entire project and the results which we obtained in the entire process. So here is the demo and the project review from our end. So we acquire the data from medical segmentation decathlon. So this is one website which is very research oriented, has many research data sets for multiple organs, not only for pancreas, but for heart, but for brain, for liver, for spleen, etc. etc. So we opened the data set from this particular website. So the entire data size was 11 GB and the data was divided into two parts, the training images and the training masks. So the difference between the mask and the training images was like the training images had all the entire CT scan or the MRI images, right? But for the mask, we had only the three classes, like the background class or the or organ class and the tumor class. So there was one distinctive difference between the two training images and the masks, and both of these could be fed into a machine learning or a deep learning model. So the size of the data was 11 GB, and we had 281 images for training and 135 images for testing the data. And each and every image was a 3D image and had extension of .nii, that is a Nifty image. The Nifty image is a standard which is followed in developing any medical application or medical image storing format. So that is one particular information about that. After having the data, we analyze the data and these are the findings which we could obtain from the data. First of all, like passing a 3D model, 3D image into a machine learning model, deep learning model is quite computationally expensive. So we decided of using a 2D images for that particular use case and developing our algorithms accordingly. So coming back to the distribution of data, like we splitted the entire 2D, like 3D images into multiple 2D image slices and then analyze the slices depending upon the target distribution. So the results were like this, like the total number of 2D slices were 26,721 of the shape 512 plus 512. And the distribution for the background class, the organ class, and the tumor class was in this particular way. So this particular graph shows us that this is the class imbalance problem with the minority classes having a distribution of say only 33 percentage of the entire data. So we had to develop our models keeping this feature, this distribution quite in mind. So after that, we found out what is the average starting and ending point for the target slices which we want to build the model. So average starting slice was the 39 slice, and the average ending slice was the 48 slice. So this approximately would give us around 9 slices per image, per 3D images. After having built the after having the data set and analyzing the data set in the class distribution, so there was a requirement of building an image processing pipeline, right? Because whenever we're feeding the data into the model, the data has to be quite accurate and efficient so that the features could be understood in an optimal manner. So we tried of building an image processing pipeline. So this is the raw image, and after building the pipeline, we are getting this pre-processed image. So we followed a total of 4 steps in the entire pipeline. The first step was equalizing the image. So this was applying a histogram equalization with the help of scikit image. And the second step was the window image minimum. So this particular feature was able to handle the pixel intensities, like the minimum and the maximum pixel intensities, and then adjusting those pixel intensities as per the image. The third step was normalization of the image. We are using a min-max scaling to convert the entire pixel to convert a single pixel for a particular 2D image. After that, we are getting this particular image. So this image is a grayscale image, and we are storing the image as a .png file for the model development process. So this is the grayscale image, and this is the corresponding mask for that, and this is the corresponding grayscale mask for the respective training image over here. So after having built the image processing pipeline, it was time to go for the model building approaches and determine which of those particular models can fare out well in the entire data format. So we opted for a multi-unit model. So this unit model is one such state-of-the-art algorithm which is used in building biomedical deep learning applications. So here we are using railway activation function, and in the output we are using softmax activation function because the number of classes is more than two over here, and the weight initialization with weight initializer we are using enormous weight initialization in all of the algorithms. Okay. And also TensorFlow has been used as the library for building the deep learning models. Also, the image sizes we are kept 128 cross 128 because of the hardware resources crunch and hardware limitations. So this is the step of loading the data into NumPy array. We are using OpenCV for that. Same for the training mask, and then we're label encoding the training mask for feeding into the data. After that, we are performing a train test split. The split percentage we are using is 30% over here. And after that, this is the part where we are initializing the loss function and the metric and the optimizer for this. The optimizer uses Adam optimizer, and the loss function is categorical cross entropy for the simple multi-unit model. And we ran this the model for batch size of 4 and epochs were selected 10. So after that, we were getting that the accuracy was 99.17%. But this shows us that the model was quite overfitting because the mean IOU for this particular use case was quite less. And also the graph is not converging. Like after the point of time, the validation and the training accuracies are say plateauing. And this is not an ideal case for any deep learning model. So the mean IOU was 0.41, largely contributed because of the class imbalance problem. And as we see that the IOU per class 2 is quite less, 0.03, which is quite less and could not be used in any application. So after that, we decided to try out with different architectures, different loss functions, and different training approaches. So we tried of using transfer learning as a methodology in which we could train the encoder using pre-trained weights and then adjusting the loss functions also. Here as well, we are using 120 cross 120 images, and the same the image loading part and the image transformation part and the data preparation part is the same as the multi-unit model. The difference is there in the training architecture. So we're using loss functions, different combination of loss functions for this particular use case. The loss function used was a combination of dice loss and focal loss. In dice loss, we are passing the class weights as 0.01, 0.39, and zero point 0.6 for the respective three classes of for background, then organ, and the tumor class. So the first backbone we are using ResNet 34, and the pre-trained weights we are using are of ImageNet dataset. And the activation function is used in ReLU, and optimizer is Adam also in this particular use case. And also the GPU which we're using is Tesla K80 on a Google Colab GPU. And the batch size here is 4 and number of epochs is 20. So after that, we get an IOU score of 0.66 for our particular data. The second architecture which we are using is Inception V3 for the same loss function combination and the optimizer combination. So we ran this particular architecture for a total of 50 epochs and a batch size of 4, which took us quite a lot of time. And the results which we are getting is that we are getting IU score of 0.7852 on the training data, and on the testing data we are getting 0.45, which is quite good IU score considering the number of epochs and the hardware crunch which we are having. And the third architecture which we used was VGG16. So this architecture is quite computationally expensive as well. So we ran it for the same loss function combination like the total loss, which was a combination of dice loss as well as the focal loss. So it was giving us a IU score of 0.7453 and a dice loss of 0.83, which is also quite good considering the data at hand as well as the hardware limitation as well. So when we visualize the loss functions and the training and validation loss functions, so we also see that this is the graph for it, and this is the graph for the resonance one. So apart from that, we also tried with the attention unit, attention res units also, but that too were not converging quite quickly. So that is the entire description of the models which we have tried till now. To conclude the entire research work, we can see that 2D approach is an approach where the spatial information between the multiple slices will surely be lost. But this particular approach has quite a good scope in understanding the features, understanding the higher level features as well as the lower level features of the tumor as well as the organ part. As we can see that a mean dice loss of 0.83 or an IU of 0.74 can be quite good for the number of data which we have. And also the data preparation in our case, like considering only the images which had the all the three classes, is one such approach which can help in understanding the tumor features. Because if you're considering the images which do not have any bag, which do not have the organ part or the tumor part in them, the model might be generalizable, but the understanding of features will be quite difficult. And this particular research work focuses on training the images which has all the three classes and is yielding satisfactory results. Also, the future scope can be termed as like the further training of the models and further extensive training and further training with 3D spatial information also. So that can result in better results and better increased metric performance over the entire course of time. So in the concluding notes, we would like to thank our guide, Mr. Sridhar Kamble, for his valuable contribution, as well as Thakur College of Engineering and Technology for providing us this platform to research in this vast AI field in the medical domain and build something which can be used in further research activities. So, thank you, everyone.